So another example of using complex numbers and complex conjugates, but this time it's a common example where you have a coefficient missing. So we have this polynomial, and they told us that 2i is a complex zero, and we need to find a. Now, if 2i is a complex zero, it means that one of the factors is x minus 2i. We also know that if 2i is a complex zero, then negative 2i is also a complex zero, and we need to find the other complex zeros. So there are two ways to do it. Either you could use a synthetic division, or you can substitute immediately. And I feel like substituting in is the easiest way to go. Because I know this is a complex zero, I can use the factor theorem, which tells me that f of 2i, so I just use the complex zero, should be equal to 0. So I'm just going to do my substitution in here. So f of 2i is equal to 2i to the power of 4 minus 2i cubed plus 2i squared plus a 2i minus 24, and I know this should be equal to 0. So we're using facts about the factors. So simplifying this out, 2i to the power of 4, well, I to the power of 4 is just going to be 1, and 2 to the power of 4 is 16. And then for this one, I have I to the power of cubed is going to be negative I. So I'll have the negative with this negative is going to give me a positive I, and then 2 cubed is going to be 8. I squared is just going to be negative 1, so we have a negative here, and then 2 squared is going to be 4, and then 4 times 2 is going to be 8. I'm doing this roughly in my head, but I would recommend that you do it slowly and on the side if you want to. And then this is going to be 2ai minus 24 equal to 0. So let's simplify the expression. So what I'm going to do is just collect the real numbers, so these first. So I have 2 times 16 minus 8 minus 24, and these three are going to give me a 0. And then I'm left with 8i plus 2ai equals to 0. And then I take a factor of I out, so I have 8 plus 2a. I know it's tempting to take another factor out, but let's keep it as such. So this is equal to 0. It means that the coefficient of the complex number is equal to 0. So again, in this position, we're using the complex factors. Now, if you use synthetic division, the remainder would have ended up looking like this, and then you should use this step after. If you've done synthetic division, then this is the next step you get to, is by taking the remainder that you have left and making it equal to 0. So I know that 8 plus 2a has to be equal to 0, and if you solve this, a is going to be equal to negative 4. So then you can check your answer. Try and substitute in negative 4 in here, and try to put in 2i inside and see what you get. Your calculator should give you the right answer. So to find the other factors, we can go through synthetic division, which would have been easier if we've done it from the beginning. So you can try the synthetic division, but I'm just going to skip through that part. And what you're going to get is so after dividing by 2i, you are going to be left with 2, negative 1 plus 4i. Remember, we're taking the terms in this position, so we're considering this as one term, one term, one term, and I have negative 12i. And the other thing I'm going to divide by, remember, if 2i is a complex root, then negative 2i is also a complex root. And so this is me solving the other part of the question, which I didn't write. So part B of the question was find all the roots. So bringing the 2 down, 2 times negative 2i is going to be negative 4i, and then these two will cancel out, so I'm left with negative 1. Negative 1 times negative 2i is going to be 2i. the negative 2i and 2i are going to cancel out, so I'm left with negative 6. Negative 6 times negative 2i is a positive 12i, which is going to be 0. So this is what we're meant to get. So it means that the last polynomial I have left is a 2x squared minus x minus 6. And I can factorize this using quadratic factorization. You will be left with this. And so my other roots are negative 3 over 2 and 2. And we have 2i and negative 2i. And you can check this using a calculator. There are many polynomial solvers in the calculator, so you can use the polysolver in your GDC. And you should keep the setting on the GDC to a complex number setting so that it could give you these roots as well.